Our presentation. My name is Nikola Bešinović, and I am at the Technical University of Dresden. We have a great pleasure to welcome Pengling Wang this time, who is a great young and rising researcher who is currently a Humboldt Fellow at Aachen University, and at the same time holds assistant professorship at Tongji University in China. So she'll be talking about great new developments on energy efficient train operation, and we'll have her shortly starting. And before that, just some rules of today's game. Basically, we are happy to get your comments and questions in the chat directly and during the presentation as well. And we will bring them to Pengling afterwards. If you are wondering, we'll have the recording available afterwards. And Pengling, apart from doing great research, she is also serving RAS community, and where she's currently the chair of student paper competition this year. So we are looking forward for new submissions. So feel free to check RAS pages for more information. And now I would like to give the floor to Pengling, and please, you can take over. And everyone, enjoy it.
Okay, thanks for the introduction. Can everyone hear me? Yes, I think so. Good afternoon. I'm Pengling Wang. I'm now visiting Aachen, and today the presentation is about energy efficient train operation and organization. So basically, I will give some introduction to the work I have done during my PhD study, as well as my postdoc study. So yeah. First, a bit introduction to this topic, energy efficiency in railways. As we are all very proud of, is that railway is one of the most cleanest mode of transportations. So if we compare railway to road traffic and air traffic, railway produce the least CO2 emissions. But somehow, as we all know, the energy is now getting more expensive, and so the government trying to transfer the passengers from private transport to the public transport. And railway seems to a very good choice, but in the future, railway will facing more increasing demand of transport. And how can we achieve the energy efficiency in railway becomes a really challenging problems. And so there are many topics, there are many strategies we can use to save energy in railways. For example, we can optimize the vehicles to increase energy efficiency in the design stage. We can improve the global design of the vehicle. We can also improve the design of individual components to save energy. For example, we can reduce the total mass of the vehicle, and we can optimize the shape of the vehicle to reduce the air resistances. And also we can improve the efficiency of the traction equipments, or we can reduce the power demand of the in-vehicle equipment such as the heating or cooling systems. So there are many technologies we can use to save energy. Or we can make better use of the regenerative energies. As we all know, most of the vehicles now are powered by the electricity, the overhead power systems. So most of vehicles are able to generate the regenerative energy when the train is braking. And this type of energy can be returned to the power system or can be stored on the trains or used by nearby vehicles. If there is accelerating or moving vehicles nearby, then this kind of regenerative energy can be used by another train. But somehow there is still a great waste of the regenerative energy because it is very expensive to have the energy storage systems, and the timetable does not really take into account the usage of the regenerative energy. So there is still great potential to increase the use of the regenerative energy. Also, we can optimize the train movement and optimize the train organization. As we all know that the most energy consuming part in railway is to move the vehicle, is to give power to move the vehicle from one location to another. And if we can optimize the train speed as well as the timetable, so we can use less traction energy, that can save a lot of money. And this kind of strategy is good because it does not require extra investment. And we do not need to put money to change infrastructures. We do not need investment to buy new vehicles. The only thing we need to do is to advise the drivers to move the vehicle in a more energy efficient way, or we can have a better, a more equal timetable. So my past PhD study has been focused on this research. My PhD study has been most focused on the eco-driving. And to discuss the eco-driving, we first need to discuss the timetable design, because we know the first priority for the train movement is to ensure the train safety, and then second, to ensure the train is moving according to the timetable. And that is good for the global optimization of the traffic, because we all know that people don't want delays. Passengers do not want delays. So the timetable is very important. And when we design a timetable, we need to define the running time between two stations. Often when we design the timetable, the running time is not equal to the minimum technical running times. That means we do not ask the train to run as fast as possible from one station to another. Instead, we often give some buffer times. And this kind of buffer time is called the time supplement. So the schedule time between two stations equals to the minimum running time plus the time supplement. And this type of time supplement is very good because it is very beneficial for the delayed trains. If one train gets delayed, it can make use of the time supplement to recover or reduce from the delay. It is also very good for the punctual trains because the punctual train can run slower to save some energy consumptions. Of course, the time supplement cannot be too long because that is not good for the train railway capacity. And so how to design the running time is also a research topic have done by many other researchers. And here I want to say that the energy efficient driving should be based on some conditions, that is trying to follow the safety rules, trying to follow the timetables. And the key for the energy efficient running is to make better use of the time supplement. So there are many different driving strategies. Here, give two examples. We can either drive as fast as possible, and this kind of strategy is called the time-saving driving strategy. So basically, by using the maximum traction or braking force and drive at the maximum speed, then we can get the minimum running time, but somehow this kind of mode is not very energy saving. So another way is that if we have some buffer time, we have some time supplement, we can make better use of those time supplements, and we can drive at a lower speed and use some coasting to save energies. And this kind of strategy is called energy efficient driving strategy. And this problem is often taken as an optimal control problem. So here gives the very basic, simple formulation of this problem. So assume one train is trying to move from station A to station B on a flat track. And the train must follow the timetable. Basically, there is a given departure time and a given arrival time. Then the objective function is to minimize the energy cost. So we can formulate that with some equations. And this kind of problem subjects to three sets of constraints. The first is the dynamic constraints. Basically, it represents the train movement must follow the Newton's second law. So we know that the train movement is affected by the traction force, the braking force, and some resistance caused by the air and the gradients and the curves. So with all those forces, the train, we can calculate the train speed and the moving distances. And that is basically what has been said by the dynamic constraints. The second set is the path constraints. It represents some constraints on the traction force, the traction power, braking power, and the riding comfort. So we trying to keep the acceleration and deceleration of the train movement within a reasonable range to make sure the riding comfort of the passengers. Besides, on the train movement, there are a set of speed limits. So in different locations, the train will have different speed limits. And the last kind of constraints is about the timetable. It shows that the train should start from the station A at from speed 0, and it should departure at the scheduled departure time and arrive at the station at the scheduled arrival time. So this is a very basic formulation for the energy efficient driving problems. And based on this formulation, a lot of research has been done, and some interesting conclusions has been found. So by using the maximum principle, researchers has found the optimal driving strategies to move a train from station A to station B on a flat track. is to accelerate the train from the stop with the maximum power and then cruising at a certain speed. And if the time is allowed, then the train is suggested to use some coasting to save energy consumptions. And when the train is approaching the stop, use the maximum braking force to stop the train. So these are the 4 driving regions that is suggested to move the train in an energy efficient way. But somehow the switching point between the regions may be different, and it really depends on the gradients, the speed limits, the given running times. So here we have an example. In this example, we can see that this example is more complicated than this one, because in this one we have a flat track, we have a constant speed limit. But in this example, we have a changing speed limit, and we have different running times, different time supplements. So we can see with in this case, with different running time supplements, the switching point of the optimal control regions are different. So, and how to find those switching point, how to find the sequence of those control regions is a bit complicated. So one of my work is we proposed a multi-phase method to solve this problem. So the basic concept is the original one is people often take this movement from station A to B as one phase because they trying to find a global optimization for this whole moving process. But somehow it is difficult because there are changing speed limits and gradients. We know from A to B, the speed limits in different locations might be different, and the gradients in different locations may also different. Also, there might some time constraints along the train movement. For example, it is possible that the train have some critical time point in the middle. For example, to passing through certain stations, then the train has to pass this station within certain time window. And to take into account that, the method we proposed is not to consider this problem as one phase. Instead, we decrease the problem into many phases, and we're trying to make sure that each phase has a unique gradients, has a unique speed limits, and has a unique time constraints. And by doing so, it is possible to formulate the problem in a more accurate way. And then we developed a certain linking conditions to, on one hand, we're trying to optimize the problem of each phase separately. On the other hand, we have the linking conditions to link all the phases together to ensure the global optimization. And the method we used is called the pseudo-spectrum method. And the idea is to transform that original continuous time optimal control problem to a nonlinear program problem. And the good thing is we get some good result with it. And that paper discussed more about the one single train, but somehow it is not enough because we know it is easy to control a punctual train, but if the train is delayed, it will easily affected by the other trains, or the delay train can more easily affect the movement of the following trains. So in case of delays, this equal train driving problem becomes a bit difficult. And how can we optimize the speed profiles of delay trains? How can we avoid conflicts between trains? Becomes a challenging problem. So what we did is we trying to take into account the train driving problem together with the traffic management problem. And this is a framework proposed by the On-Time project. So I believe a lot of people are very familiar with this framework. So in this framework, there are many control loops. The out loop is the traffic management control loop. Basically, in this loop, it takes care of the more global traffic state, and it can produce new timetable or real-time traffic plans if there are delays. And then this kind of traffic plan can be sent to the DAS system, driver advisory system, or ATO systems. And the ATO system should be able to produce the optimal speed profiles. And this kind of optimal speed profiles should be able to respond to the real-time traffic plan. And the bridge between the TMS and that system is the train path envelope. So basically, we have a new timetable, and based on the new timetable, we can compute the blocking time stairways. And the concept of the blocking time stairways, or how can we ensure no conflict between the two trains, is to make sure there is no overlaps between the blocking time stairways. So every time when we get the new timetable, a rescheduled timetable, we can generate such kind of blocking time stairways, and then we can detect a so-called train path envelope. And within this envelope, we can ensure there's no conflicts between the two trains. And also within the envelope, we can optimize the train speed profiles. And the optimized train speed profiles can ensure no conflicts with other trains. That is so-called the green wave policy. So basically, if there are no conflicts, no overlap between the blocking time stairways, then there is no red signals. So the train will always drive within the green signals. That is so-called the green wave. So based on this idea, we trying to optimize the train speed profiles of delay trains. Basically, we first calculate the optimal train path envelope, and then calculate the speed profiles within this envelope. By doing so, we can avoid conflicts, and also trying to make better use of the waiting times for energy saving. This kind of concept has also been used in the real life application. So we used this concept to develop a driver advisory system for the freight trains. This is a project we did for the ProRail. The background is that in the Netherlands, the passenger corridor is often very busy, but sometimes the freight trains need to use the passenger corridors. And for the freight trains, the driver often finds it is very difficult to find the right merging moment to get merged into the passenger train corridor, because the passenger train corridor is very, very busy. So the consequence is that the freight train often has to wait at red signals for a long time, and that is a very time-consuming and energy-consuming process, because to restart a train, and especially a freight train, it takes a long time, and also it takes a lot of energy. So ProRail proposed to develop a driver advisory system, and the concept behind this system is very simple. Basically, this app trying to monitor the real traffic state of the passenger trains, and then they set 2 points at this merging area, and if the train passenger train P1 pass this point, then this app start to count down like this, and this countdown can remind the freight trains to start to merge in. So the basic idea behind this is to help the drivers to find the right merging time window. And to improve the function of this driver advisory system, we developed a driver advisory framework. The idea is, this system should be able to monitor the traffic state of the passenger trains, and based on that, we calculate the speed profiles quickly, so we can calculate the blocking time stairways quickly. And if we have such kind of information, we can know the buffer time in between the passenger trains. And then based on the buffer times, we know we can detect the right moment for the freight trains to merge in. And this kind of detection is helpful for the freight trains to get merged into the passenger train corridor. And it is helpful for them to reduce the unplanned stops at red signals. Apart from the eco-driving, I would also like to introduce some work we did focused on the eco-timetabling. So as we all know that timetabling is also very important. As we said in the designing phase, the time supplement is very important, and how to distribute the time supplements is also very important factors. But somehow when we design the timetable, often the energy efficiency is not the first priority, because we need to take into account the feasibility, the robustness, and many other objectives, and costs, of course, and passenger satisfaction. So energy is not the first priority, but if we can adjust the timetable a little bit, and maybe that can save a lot of energy, that is also a very good thing. The work I did is to optimize or adjust the timetable a little bit, try to improve the usage of the regenerative energy. So the background is we focused on the periodic timetable. And we all know here many countries use the clock-based schedule. So with this kind of schedule, a lot of trains trying to get in a station within the same time and leave the station at the same time. The advantage is that the passengers can make use of the dual time for the transfers. This is very good for the passengers and it's very good for the station operators. But somehow it is not very good for the power system because when the train arrive at the station simultaneously, and then the power requirement increase significantly. And when the train leaves the station simultaneously, then all the trains can produce the regenerative energy, and those energy has not been used. And sometimes that kind of energy can produce this kind of peaks. And this peak is not very good, and it can damage the power system. And of course here, as we all know, many countries have the ambitions to increase the number of trains. So this kind of situation will become more and more serious. What we're trying to do is we're trying to shift the power peaks in the planning phase by optimize the timetable. And by doing so, we can also improve the usage of the regenerative energy. The idea is also very simple. We're trying to increase the simultaneous acceleration and braking trains. So we're trying to have such kind of overlaps. So when one train is braking, we have a nearby train here to accelerate. By doing so, the regenerative energy can be better used. But somehow we know that passenger may not be happy because the original clock-based timetable is very good for the passengers. They can easily transfer from the blue train to the red train. But if we're trying to synchronize the acceleration and the braking trains, then this kind of connection might be broken and passenger will not be happy. So it is necessary to take into account the passenger satisfactions when we adjust the timetable. We're trying to not make passenger. We're trying to not to break the main connections, passenger connections. The model is based on the PESP model because we are dealing with the periodic timetable. And within this model, we have nodes which represent the arrival, departure, and passing through events. And we have many links or arcs. Those arcs represent the train running, train dueling, train the headway constraints and the turnaround constraints. So we can formulate the very basic problem with such kind of constraints. Because we are, it is a timetable adjustment problem, so we add some constraints to ensure we do not change the structure of the timetable. And the things we're trying to do is we're trying to add more synchronized acceleration and braking trains. So to achieve this target, we add some links between the arrival event and the departure event of another train at the same station. So by doing so, we can calculate the overlap time of the braking phase and the braking phase and the acceleration phase. And we also be able to calculate the overlapping time of the two phases. Another thing is we try to take into account the passengers, because if we change the timetable, then the passenger movement or the passenger may use different vehicles, different train services. So we need to be able to evaluate the change of the passengers movement and also the change of passengers travel times and so on. So we extended the original PSP model by adding more passenger related events and activities. So we add some activities such as the train pass, passenger pass, passengers waiting at the origin stations, passengers in vehicles, and the passenger transfer activities. For example, here, we know that from station A to station D, passengers can use intercity directly, or the passengers can use the sprinters and make a transfer at certain stations. So all the passenger can travel in another route and arrival station D. We know for each OD, the passengers will have different passes. And if the timetable changes, the passenger may use different passes. So the model should be able to calculate which pass the passenger will use and which what is the new travel time of the passengers. So by adding this pass activity, and we can build constraints to calculate the generated travel time of each possible pass. And the generalized travel time of each pass is assumed to be equal to the weighted in-vehicle time plus the waiting at the origin station time plus the transfer times plus the transferring numbers. So by doing so, we can know the cost for a passenger to travel from A to B. And also we build constraints to ensure the passenger will choose the path with the minimum generated travel times. So this is the assumption we used. And this is assumption is for the passenger assignment. Now the model is able to calculate the overlapping times for all the possible synchronized acceleration and braking processes. And this part represent the usage of the regenerative energy. And it is also be able to analyze the passenger travel times and passenger satisfaction levels. So it becomes a multiple objective optimization problem. And what we did is we trying to first satisfy the passengers. We try not to decrease the service level, and based on that, we trying to increase the usage of the regenerative energy. And some result has been done based on the case study on Dutch railway network. So basically, it's a trade-off problem. We need to trade off between the passenger satisfactions and the energy consumptions. But the result has shown that with a little sacrifice of the local passengers, we can gain a lot of energy saving. And also the power peaks can be reduced greatly. Yes, basically that's my share of today. I shared some research I did before about the eco-driving and energy efficient timetabling. And I believe in the future, there are many more interesting topics that we can do in this for the energy efficiency in railways. That's the end of my presentation.
Great. Thank you. Thank you so much, Pengling, for this very informative and very well organized presentation. So we have several questions already, and yeah, they take us to different directions. So maybe we can start with the first one coming from Marty, and he's wondering, so most of the work has been done with fixed block signaling systems, and have you considered moving block? And in particular, have you evaluated potential savings in energy consumption? Could you comment on that?
Let me see. Energy saving. So I personally didn't check the energy saving for the moving block for the train movement under the moving block signaling system. Somehow I can comment that for the moving block, the difference between the blocking time stairways is not a stairway, instead is a very smooth path. So I think the fundamental concept is more or less the same. I did some research for the virtual, not virtual block. So the virtual block I think is similar to the moving block signaling system. So it's kind of in the between of fixed block signaling system and moving block system. So the difference between that is blocking time stairways is different, but somehow the train movement, I assume, is the same, more or less the same. Yes.
Okay. Well, maybe to add, maybe it also depends on the layout of the fixed block tracks. So if the signals are maybe closer, then the benefit of virtual or moving block could be smaller, but it may be really from case to case.
Mm-hmm.
Okay, and
yeah,
sorry, do you want to add something, or we have some more questions as well?
Yeah, please.
Okay, then maybe on regenerative braking. So what is the proportion, and how much of the energy actually goes on regenerative braking, or we actually get from regenerative braking?
How much? So basically, if the train is braking, then it works, I think around 80 or 85% of energy can be returned to the power system. That is in theory, but somehow that really depends on how long is the braking phase. So how long is the braking distance, and how long is the braking, and how many braking forces has been used. Yes, I didn't know the number. So, and the research has been found that there's great potential to use this kind of energy. So it has been said around 15% to 30% of energy saving potential can be expected if we can use this kind of energy.
Okay, and to follow up on that one, I believe you refer to passenger trains.
Yes, yeah.
So could you maybe comment on what would be in the case of freight trains? Would you expect even a bigger savings in the future? How do you see it?
You mean the regenerative energy for the freight trains?
Or in general, energy efficient driving?
Okay.
Applying to freight.
So for freight trains, I think it really depends on the, I mean, different countries may have different situations. For example, in China, we have very long distance, very heavy freight trains. So, and in some routes, there have a long slopes, downhills. So for those kind of situation, there is a great potential if we can make better of those slopes, those downhills for the energy saving. For some short distance freight trains, I don't know. I mean, maybe it is similar to the passenger trains, but I'm not sure.
Is freight to be considered as part of your research in the future? Maybe?
Maybe, but not. I haven't taken into account of the freight trains. Not that much.
Okay, and we can go to the next one. So it's coming from Milan Janic, and it's about the balance between time savings and energy savings, and how to prioritize and whom to focus on. Do you want to leave it completely to the planners and to infrastructure manager, or would you give some more expert opinion how to balance it?
Which question is this one? What is the flexibility to change and adjust timetable?
Well, kind of combining the two. So looking at the balance and on time saving versus energy saving.
Okay, yeah. So I think it's really, we need to balance, because railway train organization is not just for saving energies, also it's not just for the time saving problem. So in the designing phase, we need, it really depends. Different corridor may have different priorities. For example, for busy corridors, then to improve the capacity usage, to add more trains, then perhaps we can give less time supplement. So, but that is not very good on the one hand, because the timetable will becomes less robust and is more easily affected by the unscheduled, unexpected events, delays, such. But for some other corridors or for some specific situations, adding more time supplements is very good, because the timetable will become more robust and the train can drive in a more energy efficient way. But somehow the travel time of the passengers will be increased. So it's really a balance. It really depends, I think.
So is that a question that we as researchers should provide to infrastructure managers, or we should leave it to the managers?
That's a good question, I think. Yeah, I think we should play our part in this problem. Also, sometimes the market should also have certain rules in this problem. And sometimes it's a policy or political problems, because yeah, in different countries, there might be different strategies, different policies, I think.
Okay, so hopefully we can provide some quantitative estimates to make decisions better.
Yes.
So, okay, maybe for the next one, I would invite Marty and then Thomas maybe to just elaborate on your questions. I guess that would be the best way to go forward. So Marty, would you like to jump in?
Nicola, thank you. And thank you, Professor Wang. Actually, in the comments section, Ying Peiran put in a comment right here at the bottom that I think is a nice way of restating what I was trying to ask about, which is the subject of a space headway being modeled as the Greenway policy. And the question is whether the size of the Greenway influences the overall energy use in the system.
Yeah, I think first of all, the green wave is very good for the individual trains, because on the stop and the reacceleration process is not very energy efficient. It consumes more time and more energies. So first of all, it's very good for the individual trains. Second, I think from the global point of view, it's also very good for the global traffic, because the unplanned stop at the red signals and decelerate maybe with the yellow signals. That means that could mean more time or delay. And those delay will affect other trains. So the delay can cause the bad influence to the global traffic. So from this point of view, I think the green wave policy is also good for the global traffic.
Thank you, Professor.
Thanks for the question.
Okay, and maybe we can shift to Thomas Graffanino, who also had a comment from a Swiss perspective.
Yes, hello, do you hear me?
Yes.
Yes.
Yes, okay, thank you very much for the presentation. Yes, my question was, you show SPB figures for energy consumption, and then you study ProRail study case. So these two things were not matching for me, because they are two very different systems. So my question is, why don't you show us some ProRail figures for energy consumption?
Yes, sorry for this confusion, because this work was did at ETH when I was in Zurich, so I used the SPB picture. But somehow we find the SPB have the AC system and have this system have a high voltage, but the Dutch railway use the DC system. and is more easily affected by the power peaks. But we didn't find the power peak figure of the Dutch railway. So sorry for the confusion.
Great, we can discuss further later. Thank you very much.
Yeah.
Okay, so are there any further questions for Pengling? So if there are, feel free to also raise your hand and address them directly.
Nicola, I have another one.
Yes, please, Marty, go ahead.
Right at the beginning of the presentation, there was a reference to leaving some availability for higher speed operation in a timetable in case a train became delayed and needed to regain its schedule. How would we make this control system more dynamic rather than to just set the schedule for optimality? What are the what logic further needs to be applied for recovery?
Do you mean, yeah, like here? Yeah.
Yes.
So here, what I want to say is in case of small delays, then in case of the dispatcher didn't get involved, then the train also have certain of ability to adjust its speed and to catch up the schedule. But somehow if the delay is too big, and if the interaction between the delayed train with other trains becomes big, then I think the dispatcher should get involved to solve delays.
Yes. So if we establish a schedule that has more fault tolerance, right, that has more time available to trains to recover their schedule from delays, what is the effect on the energy consumption of that schedule? Do schedules have more or less energy consumption if they are more or less recoverable?
So I think, yes, if the timetable is more robust, but the robust really depends because on the one hand, we can add the buffer time at the rolling times. On the other hand, we can add the buffer time to the headways. So if I think if the buffer time is in the rolling times or dual times, or not dual times, in the rolling times, then it is definitely good for the energy efficient driving. But if the timetable, the buffer time is in the headways, maybe not directly good for the energy efficient driving if the train is on time, but somehow in the global point of view, if the trains get delayed, so the train, other trains has less chance to be affected by the delayed train. So it can still keep in energy efficient driving manner. That is also good for the energy efficient driving. Yeah.
Thank you, Professor. Really appreciate this.
Thanks.
Great, and
yeah,
maybe have time for a very quick one from Thomas again.
Sorry, it was not a question, but to add some results from Japan. There's interesting results regarding buffer time and energy consumption. The higher energy consumption is with no buffer time, and it decreases when we have more buffer time. And the decrease of energy consumption goes flat. So it's like 1/x function. So it means that adding many buffer time is not interesting anymore after a given moment. So that was an interesting result I never saw somewhere else. And that's what I wanted to mention to add. Thank you.
Yeah. I know the curve you have been marked. Yes, after certain point, the gain for energy saving is becoming limited.
Okay.
Exactly.
Well, thank you so much. I think we are coming to the end. I would like to thank to Pengling Wang for a great presentation. Also, thank you everyone for your healthy presentation and your healthy involvement in the talk. Thank you to Maurice Kraut, who helped us organizing and providing technical support. So we continue next month. We'll share the slides and the recording afterwards. You will receive it in your mailbox. And we are looking forward to see you again in our next webinars. So far, that's all from us, and see you all the next time. Have a great day.